My name is Qing Lu, and I'm an associate professor in the Department of Civil and Environmental Engineering. So this seminar series are co-sponsored by our department and Qatar and the USF Student IT chapter, and also 3 USDOT University Transporting Centers. And today we are very glad to have Dr. Mingyang Li from the Department of Industrial and Management System Engineering to give us a talk on the research project that is related to the transporting infrastructures. So Dr. Li is currently an associate professor in the MSc department, and he got his PhD degree from the, I think, from the systems and industrial engineering field from the University of Arizona. And his research mainly focuses on data analytics and informatics with very diverse applications in different fields, including reliability, quality, and healthcare, and homeland security, and others like engineering, transporting engineering. So he mainly develops and applies advanced statistical methods and computational tools to address some complex problems in complex settings and with very different diverse applications. And he has published many papers in a variety of high quality journals. So with that, let's welcome Dr. Li. Dr. Li.
All right. Okay. Hello, everyone. Can everybody hear me on the Teams? Okay, thank you. All right, thanks for the Dr. Lu's invitation and introductions. So hi everyone, I'm Mingyang Li. I'm an associate professor from the industrial engineering, and today I'm gonna talk about this degradation, performance modeling, and optimal maintenance planning for the deteriorating critical infrastructures. So this is the joint work with my former PhD student, Han, who is currently also a postdoc at the Civil, and also my collaborator, Dr. Lu's team, and also the Dr. Zhang's team. All right, so yeah, it's a little bit more background of myself is my research in general is the data analytics, informatics for improving performance and the decision-making of complex system at both the design and the operational phases. And since I joined the USF, I've been collaborating with different kind of domain people to improving or studying different kind of complex aging systems. So I call it aging analytics, such as aging population, aging infrastructures, and aging materials. So today I'm going to share some of the research we have developed regarding this aging infrastructure directions. Some for quick outlines. So first, I'll give a broad overview and background information. Then I'll spend most of this talk mainly talk about two topics. The first one is about from the data side. We want to develop some of the data-driven models to improve prediction of this critical infrastructure. We use the pavement degradation data as example to illustrate our ideas. And second is we look at the decision side. Okay, we want to look at the co-located the road and pipes and develop some of the optimal long-term planning maintenance models, and for this to capture this degradation uncertainty in the future, but also this interdependence between the pipe and the road. And last, I'll just quickly conclude the presentation. All right, so I think in general, as we know that serving as the backbone of the U.S. economies, these U.S. critical infrastructures such as the road and bridge and the pipe, right? They are deteriorating, becoming underperformance and functional deficient. So take the road as example. I think in the 2021, the road infrastructure has been rated as the T categories. D categories means they are the poor conditions, and more than 1/3 of the road conditions are in either mediocre or poor conditions, which dramatically increasing or significant increasing the mobility or productivity of the road users, but also there's a lot of the sustainable issues. Same thing for the pipe and the water, and the although a little bit better, they rate it as the C-, which is the C category is mediocre conditions of C-. But again, this deteriorating the water infrastructure also cause a lot of negative consequences, such as like proper damage due to this flood or the pipe breaks. or these the water quality concerns, as well as the unmet demand to the household. So therefore, on one side, there is actually the growing need or urgent need to repair and maintain a large number of these critical infrastructures. But on the other hand, in terms of the maintenance budget or investment, there is very limited, but even have the shortfall. There are all kinds of reasons for that. For example, political reasons, financial reasons, and say one example or one reason is the actually car become more efficient. We have a less amount of the gas tax. So then, which is essentially an important component for this maintenance budget. So therefore, we're working on this. Can we have the more cost-efficient maintenance plannings? So that is the main research we're targeting on. So in this general maintenance literatures, I think there is a consensus that the more proactive or preventative maintenance is more cost-efficient than the reactive. Means if we can anticipate something going to happen, which is really bad, then we can take actions in a more proactive manner. Will be more less costly. Will be less cost and more cost-efficient than those something bad really happen, and we will take actions. And for this, preventive maintenance or proactive maintenance, there are typically two topics or two parts people typically study. The first one is, given the degradation data, can you have a better prediction of the individual units in the future? So we're anticipating how their degradation performance is going to evolve in the futures, and we kind of know when they're going to hit the threshold, typically this failure threshold. For example, the pipe, if you can think of the corrosion depths is some kind of degradation measures, it keeps increasing until it reach the thickness of the pipe. Right? It's gonna breaks. And these so the first topic is about how we can have a better prediction or the data-driven modeling to characterize the heterogeneous or stochastic evolving degradation data of the critical infrastructure or component. So in the first part, I'm going to talk about that. Second part is, okay, in terms of the decisions, right? There's all kinds of a complexity regarding the decision regarding the maintenance of the co-located or complex infrastructures. How we can develop some more optimal decisions and or optimal maintenance policies to take into account the future uncertainties, and also take into account all kinds of a short-term, long-term cost related to infrastructures. So let me also talk things. We're working on both the degradation modeling and maintenance. Let me quickly talk about some of the data complexity we're trying to address for the data-driven part. So this is some of the in-service row infrastructure, I think is data, the International Roughness Index. So the higher means, the more deterioration of the row conditions. I think this is shared by Dr. Lu's team. So this is in the field. You can see all this, forget about the solid the curves. Look at only the thinner gray curves. You can see that there's different units that have a highly heterogeneous and stochastic evolving pattern of the row sections. Essentially, they're due to all kinds of factors influence the property of the materials, all kind of environmental. But in the field, there are many factors. They are really uncertain or unobserved, because sometimes, say, materials, you have to do the specific inspection on the road, which is the time consuming, but also really costly. We can collect some data for the input, but for the large number of the road, it's really difficult to get a really detailed information for all of the road with the very detailed inputs. So unlike, say, some small devices in the control environment and the lab, I can do the in-situ monitoring. I get a lot of the information in terms of the in-service, a large network of the critical infrastructure. Sometimes, the input data is really limited. So therefore, our thought is, what about I just look at the degradation output data? Okay, those degradation output data, can we have the better modeling of this data and then make the better prediction of the futures? So basically looking at this trajectory data. And there are two aspects we want to address. The first is in the conventional modeling approaches, people always assuming the ID assumption, independently and identically distributed. The first, identically, maybe the units, their data or pattern is not really captured by the single population of the distribution parameters. Maybe they're coming from the different subpopulation. There's the grouping pattern of this. So we want to first relax this, identical assumption. It's non-identical. Maybe units from different subpopulation, they have a different distribution parameters. Second is also the independent, the units within each of the the observation within each of the unit, they are like a correlated, repeated measurements. They're also dependent. So we want to really expose this independent and identical this distributed assumptions. So this is the first thing. We want to capture this the population heterogeneity. Second is think about if I have a single unit, like the one particular road, I only have one or two observations. The observation is the number of the data is even smaller than my number of parameters. I don't even have the way to really predicting that. So we are thinking about, can we handling the data sparsity of each individual road unit to borrow information of this population level. So it's more like a share information from some of the existing model, we call it offline model, and then putting that to the individual unit. So it's more like integrating the offline model with some individual data to get the online individual model. And again, we want to sequentially, when the individual unit do the periodic inspection, we want to also do this sequential learning in a very convenient manner. So this is the some of the property we're trying to address. So first is we want to characterize the population heterogeneity of this data. And the second, we want to have this kind of a individualized sequential updating of my model for each individuals. So this is for the first part, the model part, the data-driven part. Second part is also we want to look at the decision, the maintenance decisions. And here we study essentially the co-located road and pipes. So to look at their interdependency, how we can have a better maintenance decisions. Why we want to look at this co-located? Because due to the spatial proximity of the road and pipe, so one may influence the other from different aspects. For example, the traffic load from the roadside may be propagated towards underneath pipe and accelerating their degradation or the cracking, like the progressions. On the other hand, if I do some of the maintenance or intervention of the pipe, that may also block the road user, or the roadside, and influencing the mobility of the roadside. So there's both is the physical dependency from the road to pipe, but also operational dependency from the pipe to road. We're going to capture that and do this kind of a joint maintenance decisions for both co-located road and pipe. Also, we're gonna talk about we'll incorporate both the short-term and long-term cost. The other thing we want to do is, suppose I have for each component level, I have optimal decision, but at network level, I have a budget constraint. Maybe to implement each of the optimal for each component is not really affordable. Then what would be the near optimal solution we can think of? Okay, we need to prioritize multiple component co-located road and pipe based on their importance, and to select maybe not the perfect optimal decision, but some kind of near optimal decisions. So this is about the second part. So this is the quick roadmap of the rest of the slides. Is the first I'm going to talk about topic one is from data-driven modeling side, look at the degradation modeling of some kind of a field degradation data. And the second part is I want to look at maintenance planning for this co-located road and pipe. Okay, the first one, I think I introduced some of the background already. So we're trying to, this is some of the real field degradation data. We try to modeling that. There are two challenges or a complexity. The first is this is maybe not a homogeneous population. We need to consider this the heterogeneous population with a bunch of subpopulations. Each subpopulation individual from that may have a different evolving patterns. So individual within the particular subpopulation may have a similar pattern, but individual from different subpopulation maybe have a distinct patterns. So the second one is say if you give me a new individual unit, say I only have 1 or 2 points, I can using this offline model to integrate that data, individual data, and build an online model for that individual row unit. And keep sequential learning, I can keep updating my model at a very convenient manner. So this is the two major complexity or challenge we're trying to address. Here's some of the state of art in the current degradation model in general is many people assuming this the homogeneous, and there's some people do offline or online, and we want to consider both. Second, there are some of the people doing these heterogeneous populations, but there is the assumption of this, the pre-specifying the number of the subpopulation. So think about it, just like in machine learning, people do the clustering, If I want to have some data and I want to do the clustering, you need to first specify, okay, I want to cluster maybe 1 group, 2 groups, 3, 4, This is the first step. I want to pre-specify number of cluster numbers and events, and then we model estimate each of the model. And the step 2 is, okay, based on the modeling estimation results, I want to compare which one is the best, right? So it's the 2-step approach. For our formulation is we want to bypass this. We don't need to pre-specify the number of the subpopulations or cluster numbers. And we can do the 1-step joint learning. Jointly identify the number of cluster number, but also the model parameter within each of the cluster. So this is the major methodology contributions. So again, our proposed framework, we want to consider both, right, like the population heterogeneity modeling, but also the individual level. And also we want to do some kind of a offline and online data fusion, but also sequential updating for each of individuals. All right, so yeah, this is some of graphical summary of what I just mentioned about. So first this is some hypothetical data, and then we first build an offline model. I characterize how many subpopulation it has and what would be the parameter of each subpopulation. And then for any new individual, say this is the new individual, I have only a single point. I first determine which subpopulation it belongs to, and then borrow the information from that subpopulation to give the individualized prediction. So this is I'm predicting the trend. So this is the failure threshold. If the future trend hit the threshold, that is right, the failure gonna occur. So we essentially is trying to predicting the remaining useful life. And we know the remaining useful life. And before that, you can have a more proactive maintenance action, right? So those actions can be triggered. And also when you have a more sequential data of these individuals, you can keep, right, do the sequential updating. Definitely your predicted distribution will also affect it, right? It will be more precise. We're going to show that we can actually improving both the point estimation, basically accuracy, but also the variability, the precision. Okay, we can reduce the precision as well. A little bit of the more, I think, a technical part. So I think this is we essentially propose is the Bayesian hierarchical models. And the first layer, you can think of this is the road with the J's observations, which coming from some statistical models. And we want to make this H is capture the nonlinear trajectory pattern of those data, degradation data. And the sigma is capture the variability of each subpopulation. So we want, in order to make it more flexible and also to relax those assumptions I just mentioned about, right? We don't want to pre-specify the number of clusters. I want to assuming an unknown number of the cluster numbers. And I want to have 1-step joint estimations. We consider some of the Bayesian non-parametric price. So if we rewrite this is going to become called infinite mixture models. So you can think of at the very beginning, I don't have any assumption of how many number of cluster I have. It just there could be a potential infinite number of the clusters. But when the algorithm really runs, it's going to really learn in actual data how many cluster we're gonna end up with. So this is just I think is to relax the pre-specify the number of subpopulation assumptions. And to estimating this model, also there are some technical challenges we're trying to address. So here is so first we do this, the approximation is we want to keep the nonlinear pattern of the data so we use the nonlinear basis expansions. So right now, the model is the nonlinear function of time, so we can capture the nonlinear degradation trajectory. But again, we want to make our computational the tractable. So I want to make the computational part more easy and analytical tractable. So we still use the linear coefficients. So this is the linear function of beta coefficient, but it's the nonlinear function of time. So this is some of the approximation we consider. And then we're doing this Bayesian sampling because, right, in general, there's no kind of a deterministic way to really get the posterior. So here we use the Bayesian sampling. And there are 2 typical technical challenges we actually trying to address. The first one is for those parameters, you can think of this coefficients, they are highly correlated. And in the Bayesian sampling literatures, if we have a highly correlated the parameters, the algorithm is gonna either not converge or converge very late. It's really difficult to make the algorithm works. So we want to make the coefficients less correlated. So that's the first purpose. We're trying to do something. Second is, remember, we relax the assumption of pre-specified number of cluster number or subpopulations. So we can have an infinite number of parameters in our models. Okay, so definitely if it is infinite, it's really difficult for us to estimate in the real time. So we want to also handle this in the more the technical way. So regarding the first one, we will consider this the data augmentation techniques to adding some latent variables. And based on that, if we condition on these latent variables, it turns out those parameters, they are become conditional independent. You only need to using the subpopulation specific data to train or to update the model parameters. And later on, we can also specify some of the very nice conjugate prior. So you can see here, all the sampling is coming from the common distributions. Okay, you can using any programming language to do this kind of sampling routines because all they have is common distribution generators. Regarding the second part is that we have an infinite number of parameters. We also consider some of the slight sampling techniques is we introduce some of the auxiliary variable UI. And the benefits for that is essentially when we're introducing these new random variables, in practice, the number of the cluster or subpopulation we generated, it's finite, it's not infinite. So by doing this, although at the beginning, we don't need to specify the number of subpopulation, but when the algorithm runs in actual implementation, it's going to select the finite number of the subpopulation numbers. So this is how we really are addressing this, the second challenge for the estimation. So this is the offline models. Based on historical data, we want to build this the offline population models. All these equations, they are coming from common distribution. You can using any software like a function or packages to implement that. Okay. And then when we have the offline population level model, think about right now is we have a new road. I may observing one data or two data of that particular road. So if I want to predicting that, it's really impossible because I only have a 1 point or 2 points, right? The data point is much smaller than the number of parameters. Okay, can we borrow the information of the previous offline models for this individual ones? So first is give my individual data, I first predict which subpopulation this individual belongs to. Then from that particular subpopulation data, offline data, integrating with this individual data. So you do the Bayesian updating, and then you can get, okay, this is my individual parameter posterior estimate given both the offline data, but also this individual online data 2 times t. Right now, I'm observing 2 times t. And here, you can see this is our, do some derivation. You can see this is some of the closed form. You can update very like in the closed form very quickly. Again, when you observing additional data, say a t+1, t+2 to t+p, I keep observing some new data. I can keep updating for these individuals, right? So it's offline data with individual data 2 times t, and sequential observing the t+1 to t+p. I can keep updating, and this updating again is the enclosed form. It's very fast, right? So this is some of, I think, is the very nice feature for this algorithm is it can give you this closed form, very tractable sequential updating for the individual. So the individual at the very beginning, it only has 1 or 2 data. Their belief of the future or the predicted distribution is very wide. But then when you have more data, in addition to that, you have offline data, you can just reduce your variability of your predicted distributions. Okay, so this is about the. All right, let me show you some of the case studies. The case study here is we consider some of the real data of the International Roughness Index data of the set of the payment sections. And this data is shared by Dr. Lu's team. So here is, think about, this is we first get a set of the historical data. We have a population sample of the individual trajectories, and we build an offline model. Offline model is we get the grouping patterns, right? We identify what would be the how many number of groups, and what would be the grouping pattern or trajectory model parameter for each of the groups. And then for any new data, for any new road, I put into that, I can get an online individual level model for that particular road. You can do any project level decisions based on this particular road. And then the data can also keep do the periodic inspection, keep observing this new data. I can actually improving the individualized model prediction as well. So let me show some of the concrete results here. First is the, excuse me. First is the population level, right? Population offline models. We compare with, so first the data, we identify 3 subpopulations. And you can use any model-based clustering algorithms. Typically, the popular one like AIC, BIC is, okay, they assuming 1 cluster, 2 clusters, 3, 4, right? And then they estimate each of them. in the step 2 is they use information criteria, AIC or BIC, right? They choose the best one. This is the 2-step approach, and they identify 3. But our approach is you don't have to do that. You just one step. It can automatically tell you, okay, we have a 3, and also what will be the model parameter of each of the subgroup. So here we identify 3, so it's more like above average degradation. This is the medium degradation and lower degradation. And I think for a certain threshold, I think it's 180. If the trajectory hit that threshold, right, some kind of a sort failure or gonna trigger for the row side, right? All right, so this is some of the prediction. Let's first look at the prediction is more like the point predictions. I want to look at the predicted remaining useful life, right, when they hit the certain threshold against these observed ones, And we do this the 6 test unit. So let me explain a little bit of this, maybe the first 2, and it's the same like the pattern will be for the rest of it. For the first test unit 1 and 2, their degradation trajectory essentially is belong to this first group, so above average degradations. But if we use the conventional model, is ignoring the grouping patterns, I may think, okay, this unit gonna deteriorating on the average, right, degradations. So their remaining useful life their time to hit the threshold will be longer. They have optimal, like overestimating the remaining useful life. So therefore, their predicted minus observed going to be very high. So here is pretty big. But since we can identify this population heterogeneity, we can reducing that. The test 3 and 4 is that their trajectory is belong to the group 2. The group 2 is average. So that's why both the group 2, the conventional and the proposed, were similar. For last one, unit test 5 and 6, their degradation trajectory is below average. So if we ignoring this population heterogeneity, and they may think, oh, they are just still average. And the average means they're gonna hit the threshold earlier. So they're gonna underestimating the remaining useful life. And then the error will be become more negative. But we can adjusting that to back to a little bit more smaller. So this is about the point prediction. I think people really like the point prediction. Say if you read the computer science, the papers, you say mean square error, right? Well, I like the point predictions, observed minus predicted. But in addition to that, we can also give this because our output is posterior, we can also give you this variability, or people call it precisions. Okay. So here the scenario 1, 2, 3 means based on the additional data we have, you can see is the dashed curve. Based on additional data, our predicted distribution of the remaining useful life will become more and more focused, right? The precision will be more and more high, means variability is going to reduce. And also the first 2 unit, the first 2 unit, conventional approach, right? The overestimating the remaining useful life. And the last 5 and 6, they underestimate. So this is the most, like the darker color is the proposed. So the idea here is just not only we can improving the point predictions, but also we can reduce the variability. We can give the quantification of the variability of the predicted quantities, capture the predicted distribution as the whole. All right, and this is we can also do this sequential updating. So see here we look at, okay, what would be the accuracy and precisions. So without sequential, this is the solid curves. With sequential, so you're gonna have a more spike, means you reduce the variability by sequential observing more data. On the other hand, we can also have a more a less bias and more accuracy. So improving both the accuracy and precision. So this is some of the from performance perspective, some of the benefits of our proposed models. Okay, so this is, I think this is the part 1. I talk some of the data-driven modeling, and we use some of the statistic techniques to modeling that. Offline, online, do sequential, and you can see some of the benefits. And right now, the second part is let's jump to the decision side, right? For the maintenance side, can we also develop some of the decision model to help improving the overall maintenance decisions? And here, I would consider this co-located rod and pipe is because, as I mentioned earlier, due to this the design or the maintenance purposes, typically the rod and pipe, they are designed in a pretty a spatial approximate areas. It's more like a co-located areas. Due to this, the facts, okay, so sometimes if something happened with the pipe, it's gonna affecting or disrupting the traffic of the road, influence the road network performance, but also the from road side, it may be also affecting the failure or degradation of the pipe. And we want to capture this, the physical and operational dependencies, to have a long-term planning for our co-located road and pipe, to reduce or minimize the overall cost. Okay, in terms of both the maintenance cost, but also the all different kind of user cost for the road and pipe. Regarding the existing literature, I think for the general reliability engineer literatures, the many people typically study one system, or look at the independent component. And when they consider about dependent component, they not only consider a particular one, for example, the physical or operational. We want to consider both. For this, the civil part, I think also the road maintenance, they are more like work on the road, and the water maintenance work on the water side. We want to also do this to explore the potential of this to joint maintenance, right? The opportunities. So this is about the state of art. So this is the framework. So idea is to tackle this, the long-term plan of co-located, we use or consider three modeling tools together. First, with the collaboration with Dr. Lu's team, we look at the final element to look at the failure dependency or physical dependency from the road to pipe. So the first, the final element model. Second is we incorporate the final element with the stochastic model to quantify the degradation uncertainty of the road and pipe in the future, right? Say in the next 5 years or 10 years, their degradation or deterioration uncertainties. Third is we're cropping everything into the optimization models under uncertainty, right? Just we want to minimize the long-term, the cost, but considering both the short-term and long-term, and we want to determine the optimal maintenance policies. Okay, and so this is about the three major, right? We integrated three models to solving this this task. Okay, so let's just quickly step by step to look at what our model formulation will look like. The first is we do some stochastic model to capture the degradation uncertainties, right? And the so this is we consider about joint state for road and pipe, and they are discrete state. So for the continuous degradation, you can discretize that. For example, the IRI you can discretize in 5 states. For corrosion depths of the pipe, because here we consider about this corrosion degradation, the gradual degradation of the pipe, you can also discretize into 5. And after that, we also grouping the maintenance actions for both road and pipe. So different kind of maintenance action we classify into 3 groups. So first is do nothing, and minimum maintenance, and PM is perfect maintenance. Okay, is it can also affecting differently of our degradation or progression pattern of our co-located road and pipe. But here is we jointly consider that so definitely you have a higher dimension regarding the state and actions. And after that, we trying to quantify the future uncertainty for the degradation of the co-located road and pipe, right? We build the transition probability matrix, and this transition probability matrix can be learned from the data. And for example, here, the probability means that at the beginning of the T's year, and we will take, right now my conditional state as I take this particular maintenance policy actions at T, and the next year, T plus 1, at the beginning of the T plus 1, what is the probability of that conditional state is at J, right? This captures the random or stochastic degradation of any co-located road and pipe in the presence of the maintenance actions, because this is something we're gonna optimize in the later on. Okay. And then since the previous is we're ignoring this dependence from road and pipe, here is we borrow some of the final element model analysis. Is we look at how the traffic load and the different of the road conditions, and also the depth cover is going to influence the failure mode of the pipe. Here, this failure mode, we assume this is more like the sudden failure mode, right? The crack-induced failure mode. The previous one of the pipe is the corrosion gradual failure mode. So for this, the traffic load induced propagated failure mode, for pipe, it has 2 failure mode. It keep competing to each other. Whichever occurs, the overall pipe gonna fail. So we incorporating this failure, traffic load induced failure mode with the previous degradation, gradual degradation failure mode, and then we can get this overall comprehensive, what would be the pipe, a failure probability or the transition probability matrix. Also under the different of the maintenance actions. So by doing this, we are able to first capture the physical dependency from the road to pipe. And then we, based on this individual transition probability matrix, we get this the overall, right, join the transition probability matrix to capture the co-located road and pipe over any in the future time horizons. Say, assuming this the 10 years or 5 years, at any adjacent years, their transition or dynamics can be captured by this transition probability matrix. So here, you can see here for the pipe, not only it depends on its own, but also some of the road parameters, right? The traffic load, also the design parameters, right, between the road and the pipe. And after we capture this transition probability, we also trying to construct this cost. So there are all different kinds of cost. The first is the inspection cost, right, for both the road and pipe. And then we have the maintenance cost. So maintenance cost here, we can reduce that as essentially the idea is that we can reduce the repaving cost. The reason is that think about if we can do this, the repair of the road and pipe at 2 separate times. So I already first repair the road, right? Do the pavement. And then if something happened underneath that road, I need to dig it out and do the repaving. For the co-located areas, you have to do the repavings. You have to do it twice. But if we can merging that into the same time in a time period, and those repaving can be actually taken care of with the road maintenance crews. So essentially, you only have to do paving once for those co-located area. So by having that, we can reducing this not only this repaving cost, but also say the traffic control cost, also this maintenance crew cost and some kind of other equipment cost. So that is the one idea why we want to do the joint maintenance, right? We want to avoiding too much of this repaving actions. Also, traffic control can be reduced a little bit. Also, the user cost. For user cost, we consider about 2 parts. First is the long-term user cost for both the road side, which is due to the traffic delay, but also for the water side, which is the water MAP demand. So this long-term is more from the current year to the next year, the whole year, if based on the current conditions, and what would be the aggregated cost, the user cost for the road user and also for the water MAP demand. For the second part of the short term is that this is the following is if we do this kind of a road maintenance and pipe maintenance, it's gonna blocking my traffic for a couple of days. So that is the more short term. And so first one is due to the road maintenance, what would be the blockage, right? What would be the reduced affected the traffic users cost. The second whole component is depending on the layout between the pipe and the road. The pipe maintenance may be not only affecting its co-located road, but also its neighboring roads. So this is the beta quantify, right? The neighboring road, the influence magnitude. For example, here, this the form is not only I can affect my co-located road, but also other 3 roads, right? You can put them together, and this is the overall short-term maintenance cost due to the influence of the pipe maintenance actions. So having all of these components, we build together of these optimization models, right? We want to minimize the long run cost to go from time t, current time, to the end of the planning horizons, right? Say 5 years or 6 or 10 years. So our goal is that to determine optimal actions or policies for the current time t, right? Current time t, based on whatever state you have, we're gonna give you the optimal corresponding policy, maintenance policies. The goal is to minimize the expected long run cost to go. Okay, and here's all kind of this kind of cost components, and here this transition probabilities capture the co-located road and pipe. They're a deteriorating transitions, degradations. And to solving that, this is the MTP problems you can solving use the stochastic, you use the dynamic programming and back inductions. Okay, back inductions. All right, so this is some of the case study. We do this kind of a numerical case study is we assume 5 states for the road, 5 states for the pipe, and 3 actions for each of the road and pipe. So we have do nothing, minor maintenance, and perfect maintenance. And then together we have 25 state and 9 combinations. So this as the number of the state is okay. So this what we consider 5 years planning horizons. And also we do this the finite element analysis to look at how the traffic load can affecting this underneath the pipe, right? essentially at this, in most cases, it will not affecting, but under this, the row user, under this, the pipe condition is really bad at the state 4, but also at like a very high traffic load, and also maybe the bad design means the depth cover between the row surface and the pipe is pretty narrow, which violated regulation. In those conditions, we may have some kind of a failure. Right? So this is about we're cropping this information, and then we're gonna do some of a comparison with some benchmark. Our proposal is gonna compare with 2 strategies. First strategy, both these 2 benchmark is they do this individual maintenance, like separate maintenance. I road is I do road, pipes I do pipe. First strategy is for the road side. I also want to do some optimal, right? I have some optimization model to do the optimal. But for the pipe side is I do this rule-based, means I do the reactive maintenance. Only pipe breaks, I do the repair. But if the pipe deteriorating, whatever deteriorating state it has, I'm going to do nothing, right? This is typical rules like currently considered in the practice. Second strategy is okay. For road and pipe, they do independent decision, but also they do their optimal locally. And this is the strategy 2. We compare these 2 independent ways with our model. We consider the dependencies. Let's look at some of the cost reductions. So here, this the spider diagram you can see here is this is the failure state. This is the conditional state. Say here, 3 means a current state of the road is the state 3, which is the medium like a health condition. Pipe is medium health condition. Based on the proposed, what would be the total cost? And based on the strategy 1 and strategy 2, what would be the total cost? That is the long run cost from right now to the end of the 5 years. So you can see here, first, definitely our proposed have overall is more like a smaller like a total cost. But this cost reduction will become more obvious when the pipe is at the failure state 4. And we look more detailed about that. It's essentially because our actions is we tend to give a more like a higher level of the maintenance efforts. So therefore, we have a little bit more maintenance cost because we're trying to take more actions, more aggressive actions. But that will actually reduce the user cost, So let me make it more clear, maybe using the figure. So this is again we compare this our proposed and the strategy 1 and strategy 2, their optimal decisions. Okay, their optimal decisions at different health state, and this the black. So this the square area, the left hand side. That's the lower left. This means the decision for the road. This the top right is the decision for the pipe. And for many states, if they are missing here, means they are the same. For all 3 strategies, they are the same. And here the dash 1 is also they are the same. I only visualize those differences, trying to to look at the overall the patterns. So here, compared to our proposed for both S1 and S2, you can think our proposed have more darker areas. Means I tend to have a more aggressive maintenance actions, right? Why I want to do that is because think about the first reason is we consider about the physical dependency of the road to pipe. So therefore, the pipe is their failure rate is gonna accelerate in the future. Therefore, we're gonna more aggressive, need to take more proactive actions, right? This is the first reason. Second reason is we reduce a lot of repaving costs and other maintenance costs. So therefore, for the same maintenance cost budget, we are more affordable to handle more higher level of intensity of the maintenance. Third is that think about if pipe is break, especially like a state 4, if pipe is break or in a poor condition, it's going to affect not only the road side but also the pipe side, right? Or not only the pipe side but also the road side. Therefore, their negative impacts will be larger. So to just mitigate those larger negative impact, we want to have a more proactive action at higher level of maintenance activities. So that is the general the managerial insights. For example, when the road is state 4 is pretty bad, poor conditions. Pipe is state 4. Say here, for the road, we recommending the same, right? Our 3 approach. This just to do the perfect maintenance. But for the pipe, we recommend perfect maintenance, the strategy 1 recommend do nothing because the rule base says only the pipe is break, I do something, right? If it's not break, only at the state 4, do nothing. And this optimal one, but individual separate approach is that, okay, do some minor maintenance. So we want to do like a more because, right, we want to reduce actually in the long run, all this kind of user cost. This is, I think, the differences in terms of the optimal decisions from proposed as compared to some of benchmarks. And let me also quickly show you some of the, for this results is we're assuming some fixed degradation, like the dependencies. And also remember the propagated effect, the road and the pipe, there are different layout, right? We assume fix the layout and fix this, like physical dependency from road to pipe. Right now, we want to do some sensitive analysis and look at how those factors will influence our optimal decision. First is this the propagated effect. Think about this, the beta 1 means like the number of the neighboring areas you're gonna affecting by the pipe maintenance, okay? So if we're increasing this pipe, so it means if this co-located area, the pipe maintenance is gonna affecting a more surrounding road, we tend to prefer a less aggressive maintenance, right? It is intuitive because if you do something for the pipe, it's gonna affecting a lot. Maybe right, you tend to not do that much of the maintenance activities. So, and we're showing that because this the short-term maintenance cost is gonna dramatically increase due to the increase of beta. So we want to that one not dominating the overall user cost. If you want to reduce that, we have to to reduce the maintenance activities. So this is for the first factor. That is the beta. How does that will influence our optimal decisions? Second is the traffic load effect. We have a different design, like a good design, bad design, or very bad design for between the road and pipe, and therefore their degradation of the pipe can accelerate at different rate, right, due to the traffic load. So if the traffic load effect is become more and more obvious, see here, we're gonna tend to have a more aggressive, maintenance activities, to really mitigating the pipe's failure. So this is the, and also, because if we can mitigate that, the orange one is the long-term user cost. The long-term user cost due to the deteriorating pipe or accelerating failure mode of the pipe can reduce if we have a more like a higher level of the maintenance activities. Okay, so this is some of the again some of the manager insights we can actually derive from this the comparisons. And everything here is we look at the one component, right? Co-located rod and pipe. We also do this, say, multiple co-located ones. Okay, so it's multiple components. We want to look at how the budget will really influencing this like the maintenance decision, because the previous optimal decisions maybe it's good for the particular component, but see we have multiple component, but I have a limit budget. If using this optimal one, this is optimal ones with no budget constraint, definitely it's okay. But in practice, maybe it's not really realistic because we have a limit budget. They cannot really affordable to achieve all their individual optimal. Then, so this show you a different budget constraint would be their near optimal. Right? I cannot do the perfect, but given the budget constraint, I may prefer, okay, this road and pipe maybe do prioritize using their optimal. Some of them maybe just sacrifice a little bit based on their social economic importance. Say if some of the co-located road and pipe they are closer to the school or hospital, maybe I have more weights for them and to share more budget to them and let them to using their optimal one. But the other one far away from the important area, maybe use the near optimal, maybe second most like the optimal or third near optimal. So, that is ideal. But in terms of this the multi-component, again, if we compare about like alternative benchmark 1 and 2, no matter what kind of constraint we have, we still have the overall reduced maintenance cost. So it's still show the cost efficiency of our proposed work. Okay. I think that's pretty much it. So I basically talk about both predictive and the pursuit analytics for the degradation performance modeling and the maintenance planning. For the data-driven part, data modeling part, predictive analytics part, we're trying to address the population heterogeneity and individual sparsity of the data. And we can give both offline, online model, but with the closed form sequential updating. For this, the long-term maintenance planning, we actually capture the co-located road and pipe under their both physical and operational dependency but also their degradation uncertainty. So we get like a more cost-efficient maintenance planning policies to reduce the long-run cost to go. All right, so I think this is pretty much it. I know this is end of the semester, right? A lot of students are very busy preparing your exam. Yeah, hope this can be right. You can get some idea of what we did. And thank you. Any question? Thank you.
Yeah, thank you, Dr. Lee.